Section 7.3, hyperbola. And so a hyperbola is a locus of all points whose difference of distances to two fixed points called foci are always the same for each point on in an ellipse. We had the sum of the distances were the same. Here the difference. So if I take the distance from this point to this foci, subtract it, the distance from this point to the foci, then it'll be the same whenever I subtract. Of course, take absolute value, so it's always same sign. So if you take the difference between the distance to, how much further away is the longest one, longer foci from the nearer foci. So take the difference, how much longer is the distance from your position to the longer foci as compared to the nearer foci. Okay, so oops. So this is my hyperbola. Here are my two foci. If I take a line connecting the two foci, this will be called the real axis or the transverse axis. If I take the intersection between the hyperbolas and the real axis, I'll get two vertices. If I take the midpoint between the foci, I get the center. If I take a line perpendicular to the real axis at the center, so perpendicular at the center, then this will be called the imaginary axis. If, I'll have to now do this, if we draw a bounding rectangle and draw the diagonals of my bounding rectangle, the diagonal bounding rectangle go through the center of my hyperbola. Then these diagonals will be called asymptotes. Your hyperbolas will approach but not touch these particular asymptotes. And these hyperbolas will touch the bounding rectangle at the two vertices. A hyperbola is very special in the fact that it approaches but never crosses nor touches an asymptote. That usually doesn't occur, but it occurs for hyperbolas. And unfortunately, in high school, they only give examples of asymptotes when they involve hyperbolas. And so, since there's only one situation that students look at in high school, there's an unfortunate assumption that you never cross asymptotes, which is only true for hyperbolas. So each of these parts of a hyperbola is called a branch of your hyperbola. And again, this is your bounding rectangle that goes through your center, and each of your hyperbolas will approach these asymptotes. So where would you see hyperbolas? One, if you happen to have some celestial object that passes through, let's say, goes, say it's a comet that approaches the sun and it only does it once, one of its possible paths that it could take is a hyperbola. Another situation where you would see a hyperbola. In a reflecting mirror, where you have most modern telescopes, such that it involves two mirrors, one being a parabolic mirror. Let's derive the equation for a hyperbola. Okay, so suppose we have some hyperbola here, and suppose that the center of my hyperbola is at the origin, and suppose that the focal axis is the x-axis. So suppose that the focus is at the point C0 minus C0, and that I have here that the bounding rectangle is such that, well, it has a distance here of A, so that's one of the vertices, or at A, and then the other distance here from the center to the top of this bounding rectangle is B. If I look here, the circle, so it passes through the bounding rectangle and the foci. So suppose the center is at the origin, that a vertex is at plus or minus AC, and the foci are at plus or minus C0. Let's look here at this point, 0A. So distance to the foci is A plus C. Distance to this foci is C minus A. And so the difference is, well, the C's cancel. And so you just get an A minus a negative A, so that's 2A. So the difference between the distance to the foci for any point on the hyperbola is always equal to 2A. So let's use that fact. So let's take some point on the hyperbola, xy, and let's just take the difference of their distances. And so the distance from the point xy to C minus C0, the foci, is x plus c quantity squared plus y minus 0 quantity squared. Take the square root of that, add to that, the square, subtract from that, the square root of, well, the point to the foci C0. So x minus, so square root of x minus c quantity squared plus y minus 0 quantity squared. I know that well, the bigger distance minus smallest distance has to equal 2a when I'm finding the distances to each of the foci. And so I don't know which is bigger or smaller, so I'll just call it plus or minus 2a. So let's try to solve this equation. It's a radical equation, just like what we had for. And so let's bring this to the other side of my equation. So I have the square root of x plus c quantity squared plus y squared is equal to, well, plus or minus a, plus or minus 2a plus this term, the square root of x minus c quantity squared plus y squared. So squaring both sides of my equation, the square gets rid of the square root. So it's x plus c quantity squared plus y squared. equals, use the square root property, use the, no, not, use the special product formula, the fact that you can use the perfect square trinomial, that this is a perfect square trinomial. And so plus or minus 2a quantity squared is 4a squared. Plus or minus 2a times the radical times 2 is plus or minus 4a times the radical, x minus c quantity squared plus y squared, plus the square gets rid of the square root, so x minus c squared plus y squared. The y squares cancel. Let's use the special product formula, the perfect square trinomial formula. So x squared plus 2cx plus c squared. Well, the 4a squared stays the same. The plus or minus 4a remains the same. Radical x minus c squared plus y squared. So now let's multiply this out. So this becomes x squared. Squares cancel. The c squares cancel. Let's add 2cx to both sides of my equation and subtract 4a squared from both sides of my equation. So far, it's virtually identical to what we did for an ellipse. Now let's square both sides of my equation. And so, let's divide first by 4. So I get cx minus a squared equals plus or minus a times the radical. To square both sides of my equation, so I have cx minus a squared quantity squared equals plus or minus a quantity squared just gives you an a squared. The square gets rid of the square root. So let's multiply this out. So by the special product formula, I get c squared x squared minus 2 times a squared times cx plus a squared squared is a to the fourth equals, again, this was a squared. Let's multiply this out. So I get x squared minus 2cx plus c squared plus your y squared. Multiply the a squared inside the parentheses. So I get ax squared plus minus 2a squared cx plus a squared c squared plus a squared y squared. The 2a squared cx's cancel. Let's subtract c squared x squared from both sides of my equation. So this factoring out the x squared, this becomes a squared. Let's subtract a squared c squared from both sides of my equation. So this is a to the fourth minus a squared c squared, factor out a squared. So it's a squared times the quantity a squared minus c squared, plus this last term, a squared y squared. Let b squared equals c squared minus a squared. To see why you should let that, see the asymptotic analysis in like 2 seconds. So I have that a squared plus b squared equals c squared. So a squared minus c squared, that's just minus b squared. A squared minus b squared, well, that's minus b squared. Divide both sides of the equation by minus a squared b squared. So this is just equal to 1. The minus b squares cancels. So that's x squared over a squared. The a squares cancel. So it's a minus y squared over b squared. That's the equation of your hyperbola. So let's look at some asymptotic analysis of this. So let's subtract x squared over a squared from both sides of your equation, divide by -1. So I have that y squared over b squared is 1, is x squared over a squared minus 1. Now, as x gets large, well, the -1 really doesn't make any difference. If x is gigantic, then it's going to be much bigger than a squared, and then x squared is much bigger than a squared. Say that x is 10 billion times a. Well, then x squared over a squared is 10 billion squared. Subtract 1 from it. Okay, so we had derived the equation of a hyperbola. And so we had that the equation was x squared over a squared minus y squared over b squared equals 1. So let's do some asymptotic analysis on this. So let's solve this for y squared. So I have that y squared over b squared is x squared over a squared minus 1. As x goes to infinity, well, this term becomes much, much bigger than the 1. And so we have that y squared over b squared is asymptotic to x squared over a squared as x goes to infinity. Multiplying both sides by b squared. You have that y squared is asymptotic to b squared over a squared times x squared as x goes to infinity. And so y is asymptotic to plus or minus b over a times x. And so we have that y is to plus or minus b over ax. Similarly, we have for the equation of a hyperbola, whose center is hk, such that a squared plus b squared equals c squared, whose vertices are at h plus or minus a, k, whose foci are at h plus or minus c, k, whose asymptote has been translated to h minus k equaling plus or minus b over a, x minus h, has the following equation: x(h) squared over a squared minus y minus k squared over b squared equaling 1. And so we have that the asymptote, well, if you draw the bounding rectangle, you have a center at hk. You have that the distance from the center to this outer portion of the bounding rectangle is a in the x direction, b in the y direction. Then the diagonals of this bounding rectangle will be your asymptotes. The circle centered at the center of your hyperbola, going through each of those four places, those 4 points on your bounding rectangle, will give you this circle. The intersection between the line going through the center, parallel to, in this case, the x-axis, will intersect at the foci, and this, the intersection between that real axis and the bounding rectangle will be 2 vertices, 2 points, and the hyperbola will pass through the vertices and approach each of these asymptotes. Similarly, we can do a similar sort of derivation of the equation of a hyperbola. But in this case, rather than having it open to the right and left, we'll have it open up and down. So suppose that the center of my hyperbola is at hk. A squared plus b squared is c squared. The vertices are at h, k plus or minus b. The foci are at h, k plus or minus c. The asymptotes are y minus k equaling plus or minus b over a x minus h. Then the equation of my hyperbola is minus x minus k quantity squared over a squared plus y minus k squared over b squared equaling 1. You have the center at hk. You have a bounding rectangle where the distance from the center to one of the sides of the bounding rectangle in the x direction is a, in the y direction will be b. The diagonals of the bounding rectangles are my circle going through the four corners of the bounding rectangle will be will intersect the real axis at the foci, and it will intersect the bounding rectangle at the vertices, and of course at the center. Problem number 32 on page 698. Write an equation in standard form of each hyperbola described. So problem 32, the center is at 3, -5. B is 6. The area of the fundamental rectangle is 24 square units. Okay, so let's try to find the equation of this. Okay, so we must have that the equation has to look something like, okay, here, let's take it, sorry, okay, so the center is, well, is not at 0, so I'll just write it as x minus h squared over a squared, y minus k squared over b squared equaling 1. Okay. Okay. I have that, well, I know what h and k are. They're the center. So I have that h is 3, k is -5, because they were given here in the fact that the center was at 3 minus 5. Let's figure out what a and b are. And so I don't know a yet, but I'm given that b is 6. Next, and actually I don't know, one thing I don't know yet, maybe, and I'll put these down, because I don't know, oh, but I do know there are different signs. So I'll put it as a minus and plus. So I don't know yet which one has the plus or which has the minus yet. Okay, so I have that the area of the bounding rectangle, well, the area of a rectangle is, well, length times width. Okay. And so the area is the length. Well, it doesn't matter which, well, I guess I'll call this A. And so if A is given, then the length of this will be 2A. And if the width here is, well, if the distance from the center to one edge here is 6, then the whole width here is 12. And so I have here that 24 is equal to 24A. And so I have here that A is equal to 1. So I figured out what A is. And so the equation of my hyperbola will equal, I need another page. So the equation of my hyperbola is x minus h squared over a squared minus y minus k squared over b squared. That's the equation of my hyperbola. But there'll actually be two answers because I don't know where the minus sign is. And so we'll also have another answer. X minus 3 squared over 1 with the minus in front of that, plus y plus 5 squared over 36 equaling 1. And so those two answers satisfy the given conditions. Let's look at a quadratic equation in x and y. Ax squared plus bxy plus cy squared plus dx plus ey plus f equaling 0. We will assume non-degenerate solutions, meaning we don't want the empty set, a point, a line, or two lines. So if we're looking at just non-degenerate solutions, let's consider the discriminant, d equaling b squared minus 4ac. If d is equal to 0, then this equation will describe a parabola. Notice in the case that either A or C is 0, and actually I should have that B is 0. Oops. In the case that B is 0, and so B is 0, and one of these, exactly one of these, well, it'll be degenerate if there's two of them. So if I have that B is 0, and one of these is 0, then this will be the case of a parabola. If d, the discriminant, is greater than 0, then this will be a hyperbola. If b is 0 and the sine of AC is less than 0, then this is a hyperbola. So if b is 0, and these two terms have differing sign, then it's a hyperbola. If d is less than 0, it'll be an ellipse. So in the case that b is 0, if the sine of AC is greater than 0, it's an ellipse. Meaning, if there's no xy term, and the sines of the squared terms are the same, then it's an ellipse. If, in addition, these two quantities, A and C, these coefficients, are the same, then this will be a circle. So let me sort of restate that here. If I have a quadratic in two variables without this mixed term, without the xy, so if I have ax squared plus cy squared plus dx plus ey plus f equals 0, so the b term here was 0. Let's assume that not both a and c are 0, in which case we'll get a degenerate term. So if a times c is 0, then this is a parabola. So if we only have one quadratic term, this is a parabola. If a times c is less than 0, this is a hyperbola. So if the signs are different for the quadratic terms, then this is a hyperbola. If a times c is greater than 0, it's an ellipse. So if these quadratic terms are of the same sign, it's an ellipse. If they're actually equal to each other, then it's a circle.